So, good afternoon to anyone. My name is Jean-Pierre Jaspart, and I'm quite pleased on behalf of the organizing committee of this webinar to welcome you to this online meeting in which the outcomes of the FREEDAM project will be presented. Before I start my introduction, I would like first, obviously, to thank Infosteel, who helped us really in organizing this seminar today. So I would like to thank them again also on behalf of the organizing committee. To thank also the speaker, who will make this presentation during the afternoon, and obviously to thank you all who accepted this invitation to participate. Just a reminder, but I think it's done by most of you, could you please mute your microphone during the presentations in such a way that there is no noise disturbances. So, I will start the introduction. You have seen that the project we will discuss today is called FREEDAM. In reality, inside RFCS, which is a research fund for coal and steel, this FREEDAM is a real success story. First, we started a few years ago by a project which was clearly a research project where the innovative technical solutions which will be presented today have been developed through numerical works, experimentations, and so on and so on. As this project really had quite nice outcomes, the Commission, the European Commission, decided to found a so-called FREEDAM Plus project, which is a valorization project, where, as the name indicates, we had the opportunity to prepare materials for the dissemination of this knowledge. And in reality, this is the objective of the webinar today, to present you these outcomes. And last but not least, more recently, the same consortium started a third project in which a real building will be erected, building equipped obviously with these famous FREEDAM connections. So you see that at the end we will have the opportunity really to start from pure scientific works to design tools, also with pre-normative documents which will be presented, and also a sort of demonstration project, knowing that the building will be also monitored during its life, so as to ensure that things are going on quite well and hopefully according to what we expect. First of all, I will say a few words, general words, about the FREEDAM connections. These FREEDAM connections should have, and they have, in reality, sufficient capacity to accommodate high deformation which are imposed by extreme severe earthquakes, without having damages in the main structural fundamental components of the connections. Obviously, in reality, these joints have been designed for seismic action, and they are equipped with frictional absorbers, which are in reality there to dissipate the seismic energy. So we will basically focus on the seismic response of these connections. But in any way, nowadays, we all know that robustness is also another requirement from the European norms. And so, besides the seismic actions, the building could be obviously subjected to other possible exceptional actions. And we have also to take care of that. This aspect will be addressed also during the seminar. What about these connections? There are in reality two different types of freedom connections. They, as I said, use frictional devices. And for some, these frictional devices are horizontal. It's here. And in the second configuration, these friction devices are put in the vertical position. Anyway, the connection is made by first adding a haunch to the beam. This is in blue. And then the beam and the haunch are connected to the column through, on one side, a T-stub on the upper side, which is bolted to the column and to the beam, and L stubs, they are represented here on the bottom side of the connections. The haunch is made of steel, except this plate you see here, which is made on stainless steel. It's a stainless steel flange, and it will be in contact in reality with these friction pads, and it is at that place that the absorption of the energy will take place. So this is the first configuration. The second is globally the same, except, as I said, that the frictional devices are now in a vertical position. Obviously, all these elements in blue and in green will be sometimes subjected to tension, compression, because obviously through the earthquake, we will have a continuous reversal of the forces acting in the connections. Now, a few words about the project in itself, the project FREEDAM PLUS. As I said, it's a project for the valorization and the dissemination of the knowledge from the FREEDAM project. I forgot to say something, is that the coordinator partner of this project is the University of Salerno, and I will introduce one of his representatives in a few minutes, Massimo Latour, who is a member of this university, who initiated, and he's still leading this project. So, what will be discussed this afternoon? First, the connection in themselves, how they are, how they behave, all the studies which have been made to validate their use. I told you we will also introduce some pre-normative recommendations which are completely in line with the Eurocode in such a way that this material can be used right now, even if the connection for the moment are not directly, let's say, covered by the code. And afterwards, we will present a complete design manual in which the guidance, all this guidance and worked example and so on will be presented for the connection, but also for the design of the frame equipped with these connections. So we did not limit, let's say, our studies only to the local response, but to the global response of the frames. And this manual, which is available on the website, has been translated in 13 languages. So each of us, we should find normally a version which fits to our language capabilities. Another aspect, the software and a mobile application have been developed. They will be illustrated, calculate this connection, and pre-select and pre-qualify to select pre-qualified solution. It means you can directly select a kit, a full kit, according to your needs. This will be illustrated during the talk. I would say finally, but not yet, a website has been opened, provided all the information, line, ask questions, so on and so on. The address is provided here. We also, in this project, developed and prepared some videos. One of these is here in front of you. I would like just to say that during the coffee break, will run it in such a way that for those who would be interested, they could have a look at this video. A YouTube channel is also available. And last but not least, there are seminars which will be organized in all the partner countries in Europe, but should also be organized in other non-European countries, which are dedicated to the dissemination. And the Belgian one takes place today, and I'm happy that you decided to participate. These are the countries which were involved in these projects. You see that not all the European territory is covered, but a really large part of that, and obviously many different countries around the Mediterranean Sea, because they are obviously directly affected by strong earthquake conditions. The book is here. It's a French version, but it exists in all the different French versions. If we go to the chapters, you will find information on connections, but on smart or traditional connections for seismic design. Friction dampers will be discussed more deeply. Then you can find information of the experimental campaign we did on friction dampers, on connections, on frames. The numerical work is also reflected. You know, robustness means that the structure could be subjected to shock, and the resistance of these connections to impact has also been studied. Pseudo-Dynamic test on buildings, but obviously in chapter 7, 8, and 9, then for designers, you have all the recommendations to design the connection and the buildings. And finally, robustness is addressed in chapter 10. In fact, all this material should be briefly discussed and presented this afternoon, and it allows me to come to the program, the detailed program. In few seconds from now, I will invite André Plumier to make a speech on the seismic design of steel structures, which will be a general introduction to the design in this particular under this particular actions. Then Massimo Latour from the University of Salerno will introduce the smart joint solutions that exist for seismic resistant structures, including obviously the FREEDAM connection that we developed. There will be a short coffee break. After the coffee break, Tudor Golea from our university in Liege will tell you how to design the structure with FREEDAM joints. And finally, the last presentation will be by my colleague Jean-Francois Demonceau about the available tools to design FREEDAM joints. So thanks for your attention. Have a nice seminar. And as I said, I would like now to welcome Professor André Plumier. Most of you probably know him very well. He's a former professor at the University of Liege, and he's a specialist in the field of seismic design. He's still active at the European level, especially in everything which is related to Eurocode 8, seismic design, and he's also the owner of the Plumiex office here close to Liege. So, André, I give you the floor. And first, I stop my presentation. Oh, it's already done? And you can so load your presentation. Thank you and have a nice seminar to all.
Okay, so I take the floor. Good afternoon, everyone.
Your microphone is unmuted.
Oh, no, it's okay. Well, it's not indicated muted.
No, we can hear you, no problem.
Yeah, I can hear you.
On ne t'entend pas, là.
No, we hear.
We hear. They hear me.
Vous pouvez, you can start, Professor Plumier. We hear you.
Okay. I try to. Now, do you get my presentation full screen?
Perfect. Yeah.
Perfect.
Okay, so I will summarize some aspects of seismic design of steel structures. I would say in the frame of present Eurocode 8, which is a document from year 2005. So my presentation will first recall briefly what is earthquake action and action effects, how they are calculated, what is the response of structure and the meaning of ductility, then what are the design classes, what are the conditions for high behavior factor Q, where are the possibilities for local ductility in steel structures, then the rules for DCM, DCH moment resisting frames will be presented, followed by observations on beam column joints design, and some few words on structures other than moment resistant frames. And I will conclude on some aspect of this seismic design of steel structures. First, I wish to recall that sorry, but I try to have the pointer, but the system doesn't like it. Okay, I have it. So basically, the action of an earthquake is a dynamic displacement of the ground, which is imposed to the base of the structure. This results in a relative displacement of the structure, simplified presentedly here as a single degree of freedom oscillator. So there is a relative displacement of the structure itself relative to its base. This displacement is a function of the structure stiffness, or its periods T, and of the structure damping. Following this relative displacement, there are stresses and strains induced in the structure. Now, the displacement of the structure relative to its base can be reduced by either increasing damping, so having dampers in the structure, or reducing the input signal at the base of the structure, that's base isolation. Now, in Eurocode 8, there are two levels of earthquake action for design which are considered. One is the ultimate, so it's the design action under which life safety has to be assured. It's a low probability earthquake. The basic one is a return period of 475 years. For this level, members are designed at an ultimate limit state, and it is assumed or considered that at this stage, the structure will have damages, which means permanent local and global deformations and displacements. Now, besides that, there is also a service earthquake defined, which is roughly 1/2 of the ultimate one, and under which there are drift limitations imposed so that damages would be avoided. The methods to calculate action effects are basically four. The top gun is the dynamic nonlinear analysis, where the action is presented by accelegrams. The members have nonlinear characterization, and the geometry can incorporate, the analysis can incorporate non-linear geometrical effects. Second, dynamic linear analysis. Data is accelerogram, but the material is considered linear. Then there is the dynamic linear simplified, which makes use of response spectra, which allow giving the maximum expected forces and displacement in the structure. So a response spectrum is a collection of points which are found making an analysis under accelerogram of single degree of freedom system, recording the maximum value under the accelerogram and making this point in correspondence to the fundamental period of the single degree of freedom system. And doing that for a series of oscillators, you get a curve, which is a spectrum. Now, with this spectrum, you are able, once you know the period of a structure, to calculate the maximum base shear V max elastic, to which will correspond the maximum displacement. Then the fourth type of analysis is pushover analysis, which is a static push of the structure under horizontal forces up to a target displacement, which is the one calculated, as I mentioned before. So earthquake impose displacement to the structure, and if we take as parameter the displacement, the design displacement D subscript ED at the building top, well, it has been shown that this displacement is relatively independent of the member behavior, let them be elastic or elastoplastic. And for this reason, I show here the pushover analysis of a given structure, but this structure is differentiated into 3 levels of yield stresses Fy, so that you have 3 levels of member bending strength MRD. This graph presents in abscissa the displacement, where you have this target displacement DED, and ordinate is the shear resistance of the different structures that I mentioned. Now, if the structure behaves in a fully elastic way, well, the pushover analysis will just follow a line, a straight line, up to the point which corresponds to the imposed displacement. If you have low yield strength, then you will get to this displacement by an elastic plastic behavior, which express ductility of the structure, ductility being the ratio OB divided by OA. Now, when you see that, it's clear that you can reach the imposed displacement in a more economical way if you have this VRD low, because with higher ductility, the structure makes the job with less strength. So this may go to the sense of economy, to the direction of economy of projects. Now, of course, if you make a choice on the ductility and the reduction of the sections of the members, the sections which are reduced have less stiffness than the sections which was not reduced, so that the real graph between the imposed base shear and the displacement at the top is on the form which is shown here. If the members behave in a fully elastic way, you have this line, straight line. For the other type where you have ductility, this ductility is expressed by means of a force reduction factor, also called behavior factor, symbol Q. Now, this basic elastic is with Q equal 1. It is considered that any structure without specific measure will provide a force reduction factor equal to 1.5. This is what corresponds to the ductility class law of structures. So this is the red line here. If you go into more specific details providing ductility, Q increase, and you have DCM class with Q factor around 3, green line, and DCH, ductility class high, with Q equals 6, line blue here. And of course, in the behavior of the moment frame, which are shown here, well, the more ductility you claim, the more plastic hinges you must be able to form. Now, there is a distinction in the design code that you need to comply with, depending on the behavior factor that you choose. If you choose a elastic behavior, so DCL, only EC3 has to be satisfied. If you have greater behavior factor, then both EC3 and EC8 have to be satisfied. Now, the application of the DCL design in Eurocode 8 version 2005 is still limited to a peak ground acceleration symbol gamma I AGRS, which is less than 0.1 g, g being the acceleration of gravity. So the conditions for high behavior factor Q, well, they are to have many plastic hinges, so a global plastic mechanism, not a soft story, but rather a global mechanism as those which are sketched here, and to have in every plastic hinge ductility, so that you can say that they are dissipative zones in the sense that they dissipate the energy into alternate, so plus minus deformation under forces, so that the graph which is represents the energy dissipation is this parallelogram here at a given stage of displacement. What are the available mechanisms for local ductility? Well, in steel structures, there is a number of them. You can have local ductility in plastic tension, plastic compression, if the member is not prone to global instability. So this means low tenderness. You can have local ductility in plastic bending, forming a plastic hinge here. But of course, this will require that there is not an early local buckling in the walls of the sections. And this is why in Eurocode 8, there is a relationship between the behavior factors that you want to use and the class of sections that you have to use to constitute your structure in order to avoid premature buckling. So this table recalls what are the required cross-sectional class related to the behavior factors that you use in your analysis and design. So for Q larger than 4, class 1, between 2 and 4, class 1 and 2, between 1.5 and 2, class 1, 2, 3, and for less than 1.5, so the DCL type, well, all classes are possible. Other available mechanism for ductility, well, is plastic shear. It is in fact the most ductile local behavior available in steel members. If you have a panel with a height, so depth h, and the thickness t, well, this is the standard way to calculate the shear resistance of this panel. And there you have the square root of 3 from the von Mises criterion. But you can point out also that due to strain hardening, well, very soon you get a shear resistance, which is simply HT times Fy. So square root of 3 times greater than the one you calculate with EC3. And this will have an impact on the design requirements that will be mentioned later. Other available mechanisms for local ductility are ovalization of bolt holes. So this will be translated in a rule on overstrength designs of bolts in shear in comparison to the hole punching. Other type of energy dissipation system is sliding risk friction, and this will be translated into the necessity to pre-stress of bolts in order to create some friction and also to avoid shocks in bolted connections under alternate forces F in this connection. And then there is also the plastic bending or shear of components of the connections if you are able to, let's say, calculate their capacity or ductility. Now, what are the effects? Again, local ductilities. Well, if you have brittle material or welt, so base material or welt material, it's a problem to develop yielding, especially under shock. The way to mitigate that is to impose a minimum toughness at usage temperature and also weld technique and control of welds. Local buckling is against local ductility. It's a matter of classes of section. We have seen that. Plastic deformation in too narrow zones, which can reduce plastic rotation capacity. It's a matter of connection design, which can be solved also by using pre-qualified type of connections. And then problems may exist if the ultimate limit state is reached first outside of the intended dissipative zones. And this is mitigated by capacity design that we will, a notion that we will explain later. Coming to the rules for DCM and DCH moment resisting frame, well, there is a design objective, which is to form a global plastic mechanism with plastic hinges in bending in beams or in beam connections to columns, or in the case of column base, well, you cannot escape to have the possibility of plastic hinges in column at their base, or on top of columns, well, the plastic hinges may be either in the column or in the beams. It's the same global mechanism. The design requirement to realize such a global plastic mechanism is that it's to impose a certain condition between the moment of resistance of the columns and beams. Now, at each node of a moment resisting frame, or other frames, by the way, there is equilibrium. So the sum of the moment applied in the column is equal to the sum of the moment in the beams. If there is more strength in the columns than in the beams, well, the beams will yield first, and you will realize this scheme where plastic hinges are in the beam. Now, this is the more has to be defined. The imposed condition is that the sum of moment of resistance of columns be greater or equal to 1.3 times the sum of moment resistance of beams. So the more has been calibrated to be 1.3. This condition is the so-called weak beam strong columns, or WBSC condition. Note that the MRD beam may be the MRD connection of the beam to the column. Momentary resisting frames, well, their behavior factor accepted in Eurocode 8 can have the maximum values which are given there. 4 in DCM, 5 times alpha U over alpha 1 in DCH, alpha 1 being the shear strength under where a first plastic hinge is formed in the structure, and alpha U is the when the global mechanism is formed. Now, of course, if you do that, you need a pushover analysis, and it's crazy to use Q for design. So there are default values of these alpha U or alpha 1 which are given in Eurocode 8, and these default values are related to the hyperstaticity of the structure in the way which is indicated here. Now, this is not a rule, but note that moment resisting frames and by nature are flexible, so that design is often governed by drift limitation under surface earthquake, or by limitation of P delta effect at ultimate limit states, so that it's not always possible to take advantage of the largest possible values of the force reduction factor Q. Design requirements for beams and joints in moment resisting frames are as follows. First, the strength of the resistance should be greater or equal to the calculated action effects. in beams. In connections, well, if dissipative zones are in beams, the connections have to be designed considering that the plastic hinge is indeed formed in the beam, so that the design moment of the connection should be greater or equal to 1.1 times gamma OV times the calculated moment of resistance of the beam calculated with the nominal yield strength. So there has to be an overstrength of the connection with respect to the beam, and the design of the connection, so the design action effect for the joint, refer to the plastic capacity of the beam times 1.1 times a factor which characterize the overstrength of the materials which are delivered on the market with respect to the nominal yield strength. So there is a standard value of 1.25 indicated in Eurocode 8, so that finally the moment of resistance of the connection should be greater than 1.375 times the plastic moment of the beam. So this point to stress here is that joint design does not refer to the calculated beam moment, but to the plastic moment of the beam, and also plastic moment with alternate signs, which means that the design of the connection is quite different from what it would be in a non-seismic situation. This capacity design, you will also appear in the shear verification. Now, joints, first thing is to mention that if dissipative zones are in joints, the moment of resistance of the beam is not then the dissipative zone, so that it should be greater than the plastic moment of resistance of the connections amplified by gamma OV and 1.1. In such case, the design resistance of the beam refers to the plastic resistance of joint, also considering this gamma OV. Talking shear action effect, well, in a beam, shear action effect is a sum of two terms. One is the shear due to gravity load, so the non-seismic load in the seismic design situation. And the other one is shear related to this hypothesis of plastic hinges at beam ends, so that you have a graph of bending moments of the seismic situation alone, which is the one indicated here with plastic moment left and right. So that this term of shear related to plasticity in beam ends is great. And in general, if the beam section is a constant, is 2 times the plastic moment of the beam divided by the beam length. And again, this is a capacity design which substantially increase the design value in comparison to the one which is coming out from an elastic analysis with behavior factor only, not considering these capacity design aspects. Other requirements for MRF are resistance and plastic rotation capacity should not be affected by compression at shear, which is realized by complying with satisfying these two conditions. And also care should be taken about the lateral buckling of beams and the negative moment at supports, which may imply to have such lateral supports. For columns, design action effects will also consider an amplification for capacity design reason. Omega is the ratio of the plastic moment in beams to the calculated action effect, so it's greater than 1. And the term from the analysis under seismic situation is amplified by this omega, by gamma OV and 1.1, so that the action effect for design are the sum of these two terms, the gravity in the seismic design situation and the term from the seismic effect, the effect of the earthquake. So again, there is an aspect of capacity design in the design of the columns. Shear in columns should be limited to 0.5 the plastic strength of columns, and the shear resistance of the panel zone should be like this. So it means there is no capacity design in this case. And the reason for this is what I have mentioned before, is the fact that if there is yielding in the panel zone, due to strain hardening, you will very rapidly have an increase in comparison to the standard shear resistance of panel zones, so that we take advantage of that. So not amplifying here by terms like this, the calculated shear resistance based on Eurocode 3. Web panel zone, well, shear is always high in web panels, because if you have plastic hinges in beams or their connections, you have an effect like that under the seismic action effect. So there is a strong action effect in the panel, and this may require to increase their resistance by applying so-called double plate or multiplication of webs in the panel zone. Connectors, as I mentioned, we want to favor some dissipativity by having the bolt shear resistance greater than 1.2 times the bearing resistance, and this should be developed in at least one connected wall or assembly plate, and the objective being the ovalization of bolt holes. Category B and C should be used for bolting joints in shear, and there is pre-stressed connections should be pre-stressed in all connections of the main structural frame. Surface preparation may be class B, so it's not blast sanding. It can be alkalizing paint on prepared surface. Slippage in connections is allowed. This is more realistic than sandblasting. I can explain more about that. Full penetration butt welds are considered as having overstrength if there is preparation of joints, so groove machining and good execution. The yield stress of the weld material should be equal or greater than the yield stress of the bait material, and the same apply to the toughness of the weld material. The partial factors are those of the persistent and transient desired situation, and they are shown here. Some few words about beam column joint design, recalling old memories of University of Liege 1988, where many beam column joints had been tested. Capacity design of joint had been applied, and generally very dissipative behavior was observed. However, two remarks. One is that capacity design is not enough, but localization of plastic strains should be avoided. I will explain more, and you can see that the energy dissipated can be quite different in this case, so a well-designed connection, and in comparison to this one, a badly designed connection. Now, why badly designed? Because it's not enough to say that the connection strength should be greater than the beam plastic strength. You have also to consider that plastic strains should not be localized in narrow regions. Now, if you have a design like this in which you have cover plates, well, there are three levels of strength. There is the plastic strength of the beam. Then you have the plastic strength of the beam plus cover plate. And then you have a drop here. You have the plastic strength of the narrow zone here. And if a bending moment is applied, which is sketched here by this line, well, finally, the place where strains start being yield strains first will be the one where the ratio of resistance to applied is the lowest one, which may well be in these localized regions. So in such case, all the plastic extension takes place in a narrow zone. In the calculation here, it's assumed 10 millimeters with an epsilon wide about 2%. So it means a elongation of this narrow zone, which is 0.2 millimeters. So the plastic rotation, which is the ratio of this elongation to have half the depth of the member, is 1.2 millirad, which is much less than the 25 millirad which are requested for DCM design. On the contrary, if you have a complete plastic hinge, well, the elongation takes place over a length which is roughly equal to the depth or half the depth at least of the beam, so that you get much higher plastic deformations. So this is just to explain what is said in very few words in Eurocode 8. Another aspect during this research of 1988 was that for the first time was tested the idea to reduce the beam sections in order to reduce also the action effect on the connection. Now, this does not change much the structure stiffness so that it could be applied locally in order to, let's say, make better design of the connection. Now, the public acceptance about this idea in 1989 was just to say that it's anti-engineering, so it has not much success at the time. Then came the Northridge earthquake in 1994, where connections, beam column connections, were cracked or failed by hundreds. Now, the main features of these defects were local cracks in the welds, because the welds were made on a backing bar without remelting the root of the welds. Another aspect was that in the resisting sections, a bolted shear tap was mixed with welded flanges, so that in reality shear was going through the weld of the flanges, not through the shear tab. And this was an aspect of the thing. Another aspect was the low toughness of base and weld material, bed welding techniques, protection of weld by gas shield, not adequate in open wind condition, so that the design condition for moment connections in the US had to change a lot at that time. These changes were basically to copy what we had in Europe for already a decade, which were toughness requirements. Now, other aspects were through thickness tests, especially for thick sections, and conditions for the design of joints, not mixing bolted and welded connection, welding using full penetration groove weld with reinforcing fillet weld, and a specific aspect of the design of the weld access hole. Another thing was that a stress was put on the idea to separate the stresses of the connection with the stresses of the plastic hinge by moving the plastic hinge away from the column. Now, there were two ways to do that. One was to strengthen connections, and the other one was to weaken the beam. So the Liege 1988 idea, which became quite a success. Here you see some constructions in the Los Angeles area. The thing is now commonly called RBS, also dog bone. And I can say that 30 years after we did that in Liege, people are still doing some research on the best way to design dog bones and so on. Now, one question, why is this weakening of beam not anti-engineering. How is it possible to do that without losing money because you throw away some material? Well, it's not necessary to use bigger sections if you remove some material, because these reduction of section are very local, influence very smallly, in a small way, the stiffness, the P delta effect, the period of the structure, and the action effect. And also often dimension of beams and columns are decided by stiffness, so that frames do possess anyway overstrength, and losing some ultimate resistance locally is not a problem. So there is a possibility of reduction in the cost because the design action effects in joints may be reduced by up to 35–40%, which in fact gain money rather than losing some. In 1995, there was the Kobe earthquake, and there was other type of problems which I briefly mentioned. In Japan, the practice is to have tubes as columns, to have at the shop portion of beams which are shop welded to prepare so-called Christmas tree, and have on-site bolting. Now, the problem they had there was that many of the diaphragms of these tubes were not through diaphragm, so that there is a possibility of in-plane deformation, which result in uneven stresses in the weldments, so that you get the ultimate stresses at the edge of the weld very early. You get cracking, and then you lose your connection. A small remark here about a common design. In a joint of an IP to an HEB, well, if you have butt welds for the flanges, it's fine to transmit the plastic moment due to the section of the flanges. But do not forget that you have to transmit by the web the shear and the plastic moment of the web, so that finally that the design condition which has been explained before result in a condition on the web connection which should be 1.1 times gamma OV times MPLRD web, which is there. And this moment on the connection is to be combined with the shear resistance which is required there and which also is high. The implication of that is that shear tap should be really largely stronger than the web, and top and bottom web to shear tap welds are required and must be strong to resist shear. Now, some few words about other steel structures and moment resisting frames. Concentrically braced frames, or CBF. The global mechanism that you can refer to is not one in which you would buckle in the columns or buckle in one single diagonal. So it has to be in numerous dissipative diagonals. Another type of braced frames popular in seismic region are eccentrically braced frames, or EBF, where energy dissipation takes place in links connecting two triangular part, and these dissipative link may dissipate in shear or in bending. So the design objective, well, I just explained. The design condition for having multiple dissipative zones is to have regularity in the ratio of strength to action effect from bottom to top of the structure. So NRD to NED in CBF, VRD over VAD, or MRD over MAD in EBF. Now, for the other members in those structures, well, they are capacity designed with reference to the NRD of the diagonals in the case of CBF, and capacity design with reference to the shear or bending moment of the links in the EBF. A few words to say that other things have been developed about dissipative connection. The inert project, which was led by University of Liege, has been the opportunity to develop two types of dissipative connection, so the U-shaped connection and the inert pin connection, an idea by Professor Ioannidis Vaias from University of Athens. And there are rules applicable to design such connections. Now, I will conclude by giving some light on the future. The revision of Eurocode 8 is ongoing. The revised Eurocode 8 will be operational with its national annexes in 2028. That's not tomorrow. But in 2022, the part on steel and composite structures is already, I would say, 98% finalized. This section considers all the remarks and concepts which I presented before, and this new Eurocode take into account research developments in the period from 2004, so the existing Eurocode 8, till 2022, so that's today. In particular, research on full strength, equal strength, partial strength connections, specific dissipative connections like the inert pin, which I mentioned, friction connection like FREEDAM, which will be explained in the next speeches, lightweight steel structures, and also new thing, this revised Eurocode 8 provides standard data for pushover analysis. They are in the code. So thank you for your attention and, well, enjoy your meeting.
Thank you, André, for this quite clear and complete introduction to the seismic design. I think now we have everything in hands to jump to our FREEDAM connection. We know about the design requirements now they have. So I will pass the words to Professor Massimo Latour. As I said a few minutes ago, he's from the University of Salerno in Italy, and Salerno was guiding, let's say, coordinating this project. You see that he has an Italian first name, but a French name because part of the family of Massimo originates from Belgium. So it seems that I can now give him the word. I have just to say that he became slowly a friend of the University of Liege, and so we are quite happy to have it today in this seminar. Please, Massimo.
Thank you very much. Yes, it's true. I hope that I am a friend. For sure, you are a friend of mine, so I'm very happy to join this webinar today. So my origin is from Verviers, where you brought me a few years ago, so it's very nice place. So the previous presentation of Professor Plumier, I think that was setting the base for this presentation very well, because many things related to the seismic design of the structures were introduced, and I think that also the reduced beam section connection that, as explained, was introduced a long time ago in Belgium just by Professor Plumier, is setting the base for the all the developments that have been done afterwards. I think that it's basically the father of all the partial strength joints, and maybe also of the FREEDAM joints, where I'm presenting something today in this presentation. So I will touch in my speech 3 points. So first of all, I wanted to introduce something related to the behavior of traditional joints when they are designed to be partial strength, so with resistance which is lower than the connected beam. Then I wanted to present something related to smart joint solution, in particular resilient type of beam to column joints. Again, with resistance lower than the connected beam. I will present some different solution to achieve this resilience. And afterwards, I wanted to introduce some recent developments that have been carried out in recent research for typologies which are typologies of joints which are even more advanced, which assure the self-centering of the structure. So when we are dealing with the design of joint for moment-resisting frame in seismic area, the design of the joint can be carried out according to two different opposite approaches, I will say. First, which is based on the strong column, weak beam, and strong joint philosophy. So the idea is to dissipate the energy, all the seismic energy, into the beam, as it was also explained before. We have certain criteria which allow us to assure this energy dissipation in the beam. Conversely, also the current framework of the Eurocode allows, under certain assumption, to design joints to be partial strength. Clearly, there is a very big difference between one philosophy and the other, because as it was also underlined in the previous presentation, when we are dealing with the design of partial strength joints, the variability of the cyclic response is very strong and very dependent on the connection detail. So we may have different joint solution with similar resistance or stiffness, but which have very different energy dissipation capacity. Just some reference to the current framework of the Eurocode. Currently, it is possible to use partial strength joints only if the rotation capacity of the connection is shown through experimental testing. In particular, there are requirements for the ductility capacity depending on the ductility class. So it means that basically currently in the current framework is not easy to apply a partial strength joint in the everyday practice. Because clearly it is required to do experimental testing. So basically in this moment it's not easy to conceive a partial strength joint due to this limitation which are required to the knowledge of the joint behavior. In the next revision of the Eurocodes, we are going towards the pre-qualification of joints. There will be included some typologies of joints which are pre-qualified, meaning that technical requirements will be specified. And I'm happy to hear that also the friction joints will be included in this annex containing detailing rules and specific design rules for assuring the minimum rotational capacity which is required. This philosophy of pre-qualifying connection, I would say, is coming from, in this case, from the something that we are borrowing from the US practice, where pre-qualified connections are existing since many years. And there are also in these documents, these AISC documents, many different typologies of pre-qualified connection. Which some of the typology which are based on the use of smart solution, which, as I will explain later, basically imply the use of dampers into the connection, which might be yielding dampers or friction dampers. So related to the behavior of partial strength joints, first of all, I wanted to underline some of the main aspects which are involved into the behavior of a traditional configuration of a partial strength joints, and how the use of dampers in joints is justified in light of these outcomes. So when we are dealing with a partial strength joints, so meaning again that the joint is less resistant than the beam, it means that under significant earthquake, the capacity design rules are aimed to dissipate the energy into the joint. Clearly, when we are deciding how to dissipate energy into a joint, we have to clarify, first of all, how the hierarchy of the joint is established between the different joint components, because clearly we want eventually to have a weakest element of the connection, which is able to dissipate a large amount of energy, assuring also the minimum ductility. So from this point of view, it is very important to establish which are the dissipative components of a joint and which are the non-dissipative components of the joint. Typically, it was also explained in several slides of the previous presentation. Weldings or bolts are not considered dissipative components, while it is possible to rely on different sources of energy dissipation in joints, for example, the panel zone or plates subjected to bending. I wanted to show you some results of tests that we have carried out in previous years on different joint typologies characterized by similar stiffness and strength. This just to highlight how the behavior of a partial strength joint is strongly dependent on the weakest joint component. So on the elements, on the connection component, which is characterized by a lower resistance, which in turn, consequently, this implies an energy dissipation in that component. So in these first slides, I will compare you the behavior of different beam-to-column joints characterized by the same stiffness and resistance, but these joints were designed basically to have a different joint component involved in plastic range. The tests I'm showing you are tests on external beam-to-column joints, where just in the laboratory scheme, the column is horizontal and the beam is vertical. It's just to do the test in an easier way. Basically, in this test, we apply an axial force in the column with the lower actuator and bending in the beam and consequently in the joint with the other actuator, the upper actuator. So the configuration of which I'm showing you briefly some of the test results are characterized by different design criteria, which are highlighted in some of our publications, but basically they are grounded on the component method, trying to establish a hierarchy between the different components so as to have some components which are overstrength always compared to other components. So the first joint typology I'm showing you is a joint typology where the design is aimed to dissipate energy into the column shear panel. And the second connection, here I'm summarizing always the design criteria. You have the slide available on the website, but I'm not going now into the detail of the design. By the way, the second connection, which is a bolted extended end plate connection, is characterized by different approach, which involves the design of a weak end plate and a strong panel zone. This is achieved by strengthening the panel zone with continuity plate, which remove the deformability of the panels in tension and compression, or the column web panel, which is basically removing the deformability of the panel zone in shear, the column web in shear. Similar typologies have also been tested with the reduced beam section strategy to compare with the result of different layouts. All these layouts, as I've said, are characterized by the same resistance. So the strategy here implies the removal of part of the beam material to concentrate the plastic damage far from the connection. And into a last version of this, into a last connection, we are testing a solution where we have double split T-joints. So connection where the design is aimed to have plasticization possibly only into the T-stubs, which in this case they will work basically as a yielding damper, so as an element which is dissipating by hysteresis of the steel plates subjected to bending. In this video, I'm just showing the hysteretic response of the test and the video of the test, which is highlighting with the white brush removal from the joint the areas of the connection which are more stressed. So in this solution, as you notice from the distortion of the shear panel, the joint is designed basically to dissipate in the shear panel. This usually results into hysteretic cycles which are able to dissipate a large amount of energy. But on the contrary, as you see from the type of damage that we have here, clearly there might be a problem in substituting or repairing the elements of the joint, because here they involve parts of the column, which obviously are not easy to repair when a strong seismic event is occurring. This is the second solution, which I was summarizing previously, where basically we wanted to have damage into an extended end plate element. In this case, we noticed that clearly also this connection is able to dissipate some energy, also to achieve rather large ductility rotation capacity, which in any case is much lower than what we have seen in the previous case. There is a particularity is that the hysteretic cycles in this case are characterized by what we call the pinching phenomenon. So a reduction of the energy dissipation capacity, which in this case is due to plastic deformation of the bolts, and these are phenomena typical also when there are contact forces involved, such we have in this case. For the RBS joint, which is the strategy, I think the first strategy that was ever proposed for partial strength connection. Basically, we concentrate the damage all in the beam. This is a strategy which was already largely applied in practice, very effective in avoiding any problem in the joint, concentrating the damage only in the beam. Clearly, also in this case, there may be eventually a problem of repellability of the joint, but the performance from the seismic point of view of these typologies is really excellent from what we see from the hysteretic diagram, from the moment rotation diagram of this connection, where we notice always a large rotation capacity of the joint and also a large energy dissipation capacity. The last connection, the last partial strength connection, which I'm presenting now here, which is with double split joint, is interesting because it is highlighting in this case a strong column web panel and a weak T-stub, which is used to connect, in this case, the beam to the column. In this case, the T-stub is working exactly like a yielding damper. So basically, we dissipate the energy to the yielding of the plates. This connection is already highlighting an advantage, which is practical and technical, which is eventually the repairability of the element, because in this case, we imagine it is more efficient and more easy to be substituted the T-stub, which is the only source of energy dissipation capacity. Nevertheless, on the other hand, if we look at the hysteretic diagram again, compared to the case where we dissipate energy in the column web panel or into the RBS or into the beam, we may be able to achieve a large rotation capacity, because in this case we notice this is about 70 milliradians, which is much larger than what is required by Eurocode 8. Nevertheless, the energy dissipation capacity is not optimal because it is still characterized by some pinching phenomena. If we compare the behavior of this connection, which I underline again, they are characterized by the same resistance, but as we have seen, different energy dissipation capacity, which is just the result of the hierarchy that we establish in the design of the joint components of the different connection, making a kind of ranking of the energy dissipation capacity of the different connection. The RBS will be the winner of this competition, which is not a competition, but is just to give general understanding and general information about the behavior of joints, while the column web shear is also a component, and so connection designed to dissipate in the column web are typically able to dissipate a large amount of energy, but obviously in both cases we might have a problem of repairability, more in the case of the damage in the column web shear, while the connection which are dissipating in T-stub or end plates, in bolted plates, are able to dissipate a large amount of energy, but typically much lower than what we can achieve with the other solution. But there are a set of problems that in any case we immediately highlight when we see at the behavior of these joints, which are let's say the current partial strength joint solution, the more traditional partial strength joint solution. So we have noticed that in any case we have always the yielding of some elements. Obviously, this yielding will happen only in case of ultimate limit state condition. Nevertheless, there is also the need, or even more today, which we are talking a lot about the sustainability of our construction. Obviously, a consideration is that the repairing of this element might be, in many cases, difficult if the designer is not considering, when he is designing the joint, this aspect also. So since the repairing can be very difficult, obviously the resilience and the repairability of the structure will be normally very, very low or very difficult. Additionally, there is a problem which is highlighted by all this connection, is that normally the plastic damage, when the plastic damage will occur into such kind of structure, typically it is expected to have a significant out of plumb deformation of the frame, meaning that the frame will not return to the initial position. Therefore, there is also a problem of recentering of the structure. So in any case, there are a lot of economic losses which can be still produced by the current design rules. And obviously this can result in direct losses, so the need to repair the building, but also indirect losses because clearly a significant damage in a structure will most likely result into the interruption of the building functionality. So the new approaches, especially for the high hazard countries, are currently following the idea to develop new joint solution based on the partial strength idea, but undergoing a limited or negligible damage. This is the case of the joint solution, which is the main topic of the workshop of today, which is the FREEDAM joint, where basically, compared to the traditional typologies, through the addition of a friction damper in the beam to column joint, basically we are able to substitute the traditional dissipative area with an alternative dissipative area, which is a friction device. This strategy can be fulfilled also with other type of devices, just also yielding devices. The concept is that a joint, to be resilient, has to be designed in such a way that it doesn't need any repair, or if there is damage into the connection, the damage has to be easily repairable. So there is a great wealth of typologies of innovative joint topology. So if you look at the research that are being done since at least 10, 20 years, there have been a lot of proposals for resilient connection typologies. More classically, these proposals are regarding the possibility to include into the connection, into the joint, some yielding dampers. This is the case, for example, of the slit damper connection, which is reported here, where basically the beam is connected to the column with an upper T-stop, which is fixing a center of rotation into the connection, so as to dissipate in bending into a slit damper, which is a device, a yielding device, able to guarantee a sufficient energy dissipation capacity and ductility. There are many other examples of this strategy. What is changing in one case from the other is just the typology of damper. So there are connections which are employing T-stops with reduced beam area in the web, dissipating in tension and compression like a BRB in this part. There are proposals of inclusion of BRB, which are buckling restraint braces in connection, or also proposal of inclusion of viscous or friction of viscous or lead extrusion dampers into joints. All these strategies, basically, they all achieve the same objective, which is concentrating the damage into an element which is able to dissipate well, and an element which can be repaired or substituted very, very easily. In the US, there are also companies which are selling this solution. So we want to have in Europe also similar things, actually. And this solution, for example, here, this is the case of a famous United States company, which is basically selling partial strength solution, which is employing as a yielding damper the same concept I've shown you in the previous slide. This type of joint is also contained in the pre-qualified list of connection in the US practice, and very soon we will have something similar into the Eurocode, which is something which is a great benefit for the designer, that will have many information related to the design of joints. This is another concept that was presented about 13 years ago in the University of Salerno, which is based on a similar approach from the other connection which I've shown you before, but basically is modifying, just cutting the plates with a particular shape, the capacity of these joints to dissipate energy. basically cutting the plates in such a way that a better spread of plasticization can happen into a plate in yielding. Comparing this solution, which is based again kind of yielding damper in a traditional beam to column joint layout, we notice the possibility to increase the energy dissipation capacity, so the low cycle fatigue resistance of these typologies, basically doubling the energy dissipation. So the performance in terms of energy dissipation capacity was doubling with a very simple approach. Now I want to go to the main topic of this of the workshop, which are the friction joint. Friction joints were developed starting from a work of Popov.
No.
Sorry. Okay, so they were developed initially in a work of Popov during the 90s, and subsequently they were studied very deeply by Professor Charles Clifton at the University of Auckland and by all his research team, and they are still doing many studies on these typologies. I will say that basically the path that they were following in the development of their typologies is not very far from what we are doing in the FREEDAM project, because initially they started with a research project and then a pilot project, which is the Tepuni building, which is reported in this slide. So this is a dormitory building for the University of Auckland. So it's not very different from what we are doing in the University of Salerno. And this building was implementing the first type of friction connection, which in the case of the joints conceived by the research group of the University of Auckland are very simply realized with an asymmetric friction connection, which has a behavior which from the point of view, technical point of view, is not optimal because the dissipation is happening with an asymmetric behavior. Nevertheless, it is very simple from the technical point of view. What are the key benefits of this technology, similar to what we have done in FREEDAM? I will say that the most significant benefit is to the possibility to decouple in the design the strength and the stiffness of the structure. Why? Because this connection typically behave as rigid joints, so they behave similarly to a moment resisting frame with welded joints, for example. Okay, so a continuous frame with rigid joints. Nevertheless, it's possible to calibrate by just adjusting the preloading force into bolts the resistance of the connection, so the partial strength level that we want in the connection, basically tuning the resistance of the structure as you want. From this point of view, the objective that this joint is achieving, I see a lot of similarities with the reduced beam section, because we adjust the resistance, in that case reducing the area of the beam, in this case is tightening properly the bolts. The joint is rigid, so the behavior basically will be very similar to that of a moment resisting frame with rigid joints, but with the possibility to decide basically what is the resistance of the structure. The other advantage is clearly that since this connection is able to accommodate a very large rotation by just sliding into a slotted hole connection, it is possible to basically have high rotational capacity, even larger than what is the minimum required, just very easily, just calibrating the length of some slotted holes. Two projects have been done. Basically, the research project and dissemination project is now coming to the conclusion with this workshop that we are doing currently. And I wanted to just explain something about the behavior of these joints. We have tested during the project two different configurations of friction joint, which are those reported here. Basically, a configuration where the friction damper is parallel to the flange of the beam, another configuration where the friction damper is vertical, so parallel to the beam web. The idea is very similar. There is not conceptually any difference in one case or the other. There are some specific aspects which are involved in the design, which may be accounted for into the two different configurations with specific detailing rules, which we have established during the project. From the point of view of the design of this connection, reality is not different from the typical concept that we apply into any capacity design approach. So basically, the idea here is reversed, because typically we design the beams, which will be our dissipative zone, and then we overstrength joints and columns. In this connection, we establish a different hierarchy. So we want to dissipate into the friction damper. So we will design the friction damper to slide at the ultimate limit state condition, not to slide into the other loading situation. Once we are able to establish the overstrength of the friction damper, this is a parameter that was studied during the project, you may be able to design all the remaining parts of the structure. So the hierarchy is different, the joint is the dissipative part, the beam and the column will be designed to be overstrength compared to the joint. From the many examples that we have carried out, we have shown that it's very easy in reality to overstrength columns and beam with a pretty straightforward design procedure. The result that we obtain in terms of also of weight of the structure is not very different from the traditional design approach. So what we have here is just higher resilience for the same cost. This is the behavior of the two typologies. So what we observe here is that we are able with this connection to achieve really very wide regular cycles and very stable. So this connection basically dissipates the largest possible amount of energy, which is what we have with the rectangular hysteretic cycle, with a resistance which can be very easily predicted. So we have established obviously a set of design rules. Maybe something is also reported in the next presentation with this I don't well remember, but in any case there are the informative documents of the project which are available on the ECCS webpage, where you can download and read many information related to this joint. When we compare the behavior of this connection to the behavior of all the previous joints that we have seen before, here we observe a larger energy dissipation capacity, much larger energy dissipation capacity. This highlighting also the possibility to have more favorable energy dissipation capacity for the whole structure. These results were reflected also into not only the component tests that we have carried out, but also in tests on real scale structure. In particular, we have performed at the end of the research project a test on a frame of 2 stories with 1 span. The test was carried out with the so-called pseudo-dynamic testing technique, which is a quasi-static technique where the matrix of damping and the masses are simulated, while the restoring force of the structure is measured directly during the test on the specimen. This is just to give you an overall view of what we have achieved. So you will notice the sliding on the FREEDAM joint at a certain point. What is important to highlight here is not that the performance of a structure with friction joint is much different from the performance of a traditional structure, but what is important to highlight is what is the result at the end, because a structure with friction joints, with free from damage joint, this is how we have called this connection, will result in a structure which basically is not showing any significant damage. So a structure where possibly the only small damage may be into the loss, may be translated into a loss of preloading of the bolts, into some damage into a friction plate, a damage which in any case will be always easy to repair. From the point of view of the overall performance, what we have noticed is that since there is a larger energy dissipation capacity, which is resulting into a larger equivalent damping of the structure, typically a structure with FREEDAM joint is giving rise to a reduction of the displacement of about the 35%. Nevertheless, a big problem is that these structures are not self-centering, which is what you notice when you see in this diagram that there is a residual displacement in the building. So we are doing also some other works, and some other works have been done also by many other researchers on the problem of self-centering steel structures. This is studied in different ways on different levels. I wanted just to give you a few slides about what we have done on this topic and what we want to do maybe in future research project. A possibility is to facilitate to improve the self-centering of a structure through the column bases. The column bases show all the same limitation that we have for the beam to column joint, because clearly we may have full strength or partial strength column bases where damage may be into the column, into the column or into the end plate of the column base joint. The drawbacks and limitations are the same. So the damage also in this case will be difficult to repair. So there are a set of approaches which are being recently studied for the self-centering of the column base joint through the introduction of post-tensioning forces. There are different applications, again, employing yielding dampers or friction dampers. In the University of Salerno, this basically during the research project FREEDAM, this activity was done. We have been studying the possibility to create a dissipative splice, dissipative column-based splice, again with friction damper and with a system of elastic bars which are properly designed to self-center the column-based joint. The concept here is that we dissipate the energy with the friction damper, we self-centering the column-based joint with an elastic force which is always applied by a threaded bar, but it can be also a PT bar, which is initially post-tension to have a decompression bending moment into the connection. Having a self-centering joint will facilitate the self-centering of the whole building. This is the typical objective of design of a self-centering joint. Basically, we want to have a decompression moment. Having a decompression moment which is given by a threaded bar will result in a hysteretic loop, which is defined as a flex-shaped hysteretic loop. Basically, what we have is a connection which, during the hysteretic behavior, will always pass through the for a zero rotation with a zero bending moment. This makes this connection self-centering. There are certain design criteria which I'm not at all going into the detail now. I want just to show you the main, some experimental response of this joint. This video, I'm sorry, because it's not of very good quality with some problem with the recording. But in any case, the video shows the concept of this connection, basically under bending into the column. This connection opens a gap into the splice, dissipating the energy by sliding off the friction damper, and returns back to the initial position due to this kind of tying force, which is always pulling back the connection to the initial position with about zero bending moment for zero rotation. This is what we obtain. Again, some capacity to dissipate. A behavior which, in any case, in this case, is characterized by this specific property, which is the self-centering capacity. This was demonstrated, this self-centering capacity for these typologies was demonstrated again with some cyclic tests, also some pseudo-dynamic simulation. We have done also simulation of structures employing column-based joints and friction joint in the elevation, without any self-centering capacity in the beam to column joint. The analysis show that employing a self-centering column-based joint allows to have the self-centering of the whole building for structure which are up to 3-4 stories, not larger than that. This self-centering capacity is observed in these diagrams. These are the displacement during a time history analysis, so what we should observe under a seismic event for 2 different stories of a building. For a traditional moment resisting frame, not traditional, moment resisting frame with friction connection, which is the red line, which is not able to go back to the initial position, compared to the same frame where a self-centering capacity is provided to the column-based joint. The difference is that if we start from initial position, after the sway displacement that we usually observe during seismic event, in this case, the structure will be able to go back almost to the initial position at all the different stories. So what is coming next, as it was kindly introduced by Jean-Pierre in the introduction, now we are working with the same team, the original team of the FREEDAM project, to a pilot and demonstration building. which will involve the design of a 3-story building in the campus of the University of Salerno. It will be a real building, a proper building that will be used as a laboratory and for office. So our idea is to complete, and so we have to actually, it's not only our idea, but we have to complete this project by 2024. Next year, we should start with the construction. We are now in the engineering phase, so we are designing all the elements. There will be, so this project will be a little bit a state of the art from many point of view, from the point of view of the seismic resilience, but also from the point of view of the strategies that will be implemented for the sustainability protocols that will be applied in this building. So I've concluded. I don't know if I was taking more time from what I have, but in any case, I thank you everyone for the attention, for attending the webinar. Thank you.
Thanks, Massimo. So hello, we are now back to our seminar. The next speaker is Tudor Golea. Tudor Golea is a PhD student who is working since few years at the University of Liege, and he's working in the field of robustness. But he got his degree in Romania, and he worked in design offices for some time before being PhD student in Liege. So we thought that he was really the right person to explain us now how to design, because of his personal experience, obviously, how to design a structure, in this case, equipped with FREEDAM joints. So please, Tudor.
Good afternoon, everyone. I will try to share my screen directly now. Can you confirm that you see it?
Good.
It works. It's okay.
Yes. So since Professor Jaspart already introduced me, I would like to get straight to the point. And we are going through a worked example on a structure equipped with FREEDAM joints. We are talking about a moment resisting frame equipped with side joints. And the design of this structure will be carried out first of all for gravity loads only, after that for seismic actions according to Eurocode 8. And we are going to introduce you to some robustness related investigations based on this case study structure. And after all, we are going to conclude based on this worked example, what are the benefits of this type of joints on the seismic behavior of these structures and their robustness as well. Therefore, I will try to go with you now briefly through a worked example on an MRF designed according to Eurocode 8. And the example will illustrate step by step the design procedure for such a structure. And what is worthy to notice is that this structure is being designed for ductility class 3, which is the most exigent requirement in ductility as given by Eurocode 8. Therefore, we are going to start by presenting the main characteristics of the structure. And here you can see the plan view of the structure. And what you can notice is that the perimeter frames are the lateral roll resisting frames. So these frames are, in fact, the frames that are supposed to resist the lateral loads, here the seismic action, while the inner base of the structures are pinned frame, the beams are pinned, so they are designed only to resist the gravity loads. Therefore, in order to design the lateral frames as lateral roll resisting systems, we are going to consider that they have a tributary area, or the mass, the loads that are coming from the rest of the structure are going to be transferred to these perimeter frames. The studied structure is designed to be for building, office building. Therefore, according to Eurocode 0, it is categorized as the category B structure. And the steel grade used in all the elements of the building has been S355. What concerns the elevation of the buildings, you can see that we are talking about a low-rise frame, which is a 4-story height, and each story has a 3.5 meter height, while the spans on both directions are 6 meters. What you can see here on the right, which is designated as a leaning column, it's the It's the way we are considering in the seismic design the tributary area or the mass and the loads coming from the rest of the structure that are assigned to this leaning column, and in a plane analysis they would consider indirectly the action or the influence of the rest of the structure on the perimeter frame. Obviously, as you can see, based on the location of the beams on the secondary beams, the loads that are acting on the perimeter frames are different by their direction. Therefore, in the X direction, we'll have a distributed load on the perimeter beams, while in the Y direction, because of the position of the secondary beams, we will have some concentrated loads at from 2 to 2 meters along the beam. So, as you already are familiar with the design, we are for sure starting with the computation or estimation of the loads that are acting on the structure. Therefore, we are going to assume that the permanent structural load that is distributed on the floors of the structure is 3.25 kN per square meter. This comprises the self-weight of the elements and some of non-structural permanent loads, which are coming from the insulation or the floor systems or the ceiling, which is 0.75 kN per square meter. And in conclusion, these permanent loads are leading us to a permanent load on floors and the roof of 4 kN per square meter. While on the perimeter frames, we are going to consider also some loads, permanent loads coming from the external loads, from the facade loads, walls that are 1 kN per square meter of the facade. The live loads are considered according to Eurocode 0 and 1, corresponding to an office building, which in this case we considered as being 3.5 kN per square meter, while for the roof, a live load was considered as 3 kN, being lower than the current floors. And in the ultimate limit state combination for gravity loads, this leads to current floor load of 10.7 kN per square meter, while for the roof it's around 10 kN per square meter. Hence, based on the previously estimated loads, we can now design the beams for the gravity loads, and these are going to be the interior beams, which are supposed to take only gravity loads. And you can see that by distributing the previously estimated loads on the beams, we reach a bending moment of 96 kN per meter, which in terms of resistance requirements would lead to an IP 220 profile, which is once again made out of S355 steel. But based on the requirements of vertical deflection, maximum allowable deflection, this profile has to be increased up to IP 270. For what concerns the primary beams, based on the previously already estimated loads coming from the internal secondary beams, the maximum bending moment acting on the primary beams is around 256 kN per meter, and this gives a strength requirement of corresponding to a profile of IPE 330. But once again, based on the requirements of the vertical deflection, we had to increase this profile up to IPE 360. Therefore, now we are able to compute the loads that are acting on the perimeter frames based on the previously designed already beams for inner base. And here you can see that the load pattern is different for the two directions, as I said before. For X direction, we have uniformly distributed load, and with some point loads coming from the beams to the column, while on the Y direction we have this capital P loads coming from the secondary beams, while the capital FC1 and FC2 are the loads coming from the primary beams directly to the column. Therefore, if we are going to refer now to the overall loading scheme of these frames, we are going to see that they differ on both directions. And you can see that Okay, here it's you can see that on the bottom side of the slide, we have the loads on y direction, and they are going to lead us to a greater requirement in strength for the y direction beam. Therefore, from now on, we are going to design this frame on y direction, and we are going to assume that it's going to be the same for each direction. So we are going now to start explicitly by designing the structure for seismic actions according to Eurocode 8. And here the design standard states that there are different requirements or performance targets to be satisfied. And this target performances correspond to different seismic intensity, which Eurocode 8 classifies as frequent earthquakes, occasional earthquakes, rare earthquakes, or very, very rare. And for this type of earthquakes, there are 4 corresponding limit states. The fully operational limit state is obviously the operation, the limit state in which the building is correspond to already a damaged building that has been subjected to the seismic action. And here we have the damage limitation limit state, the significant damage limit state, and the near collapse limit state, which is the one that is going to be under consideration for very, very, very rare earthquakes. It's important to state that for to design a structure against the seismic action, we are going to consider now the already introduced concept of response spectrum. And Professor Plumier has been presenting already the elastic response spectrum. But as you can see that we have here 2 types of spectrum to be considered. And one of them is the design spectrum corresponding to the operational limit state. So you can see that it is less demanding than the one corresponding to the significant damage limit state, which is in green here. While considering the behavior factor of the buildings, of the structure here, we can reduce this elastic response spectrum such that we consider the dissipative capacity of the structure. And you can see in the second figure that the elastic response spectrum corresponding to the significant damage limit state has been reduced significantly based on the behavior factor, which in this case it's around 6.5. So we are going to reduce the elastic response spectrum, assuming that our structure will undergo plastic deformations. And so we are going to take into account the ductility of the structure and therefore design it for a lower seismic intensity, that's being the reduced spectrum. While for the dissipative zones, which are here the FREEDAM joints, we are going to design these dissipative joints based on the operational limit state. And why we are doing that? Because even though the design standard doesn't state this, these frictional devices, they are intended to dissipate the energy through friction. But for very frequent earthquakes or for lower seismic intensity, we are intending to not activate these dissipative devices, and so the structure will respond elastically to it. Therefore, we are going to design the dissipative zones here, the FREEDAM joints, according to the operational limit state design spectrum, which is not reduced, which is an elastic response spectrum, while the check for the non-dissipative members and the drift, interstory drift checks will be done taking into account the dissipative characteristic of the structure, and therefore designing the structures according to the reduced response spectrum. In order to design the structures explicitly, they were modeled in the SAP 2000 software, which allows modeling the elements as linear elements, allows integrating the nonlinearity of the material, nonlinearity in terms of geometrical discontinuities, and in this software, the joints were modeled as being rigid zones with account for the end length offset. And you can see that on the right of the slide, these joints were, or the joint zone has been modeled taking into account the difference in the stiffness of the beams. And here you have a cross section through the joint zone, and you can see that at the bottom of the beam we added an element, steel plate of 260 millimeter height, which simulates the haunch of the FREEDAM joint, while the column web panel in shear zone has been modeled according to its stiffness, so that we can simulate accordingly the flexibility of the structure. In order to start explicitly with the seismic design, we have to take into account the imperfections, the initial imperfections. Why? Because these imperfections can have a cumulative effect with the horizontal loads that are induced by the seismic action. And even though the seismic action can have more components, meaning a vertical component and a horizontal component, usually we are taking into account the horizontal component as being the most depending. And given the fact that the seismic action will induce significant lateral displacements, when we are going to consider the initial imperfections, these are going to amplify somehow the demand in the structural design of the structures. Therefore, to integrate these initial imperfections in the structural model, you can see that Eurocode 3 allows to simulate these imperfections through equivalent forces, which are computed based on the initial imperfection phi, or phi here, computed based on the number of columns in a row that are going to sustain the lateral load, or that are going to be assigned the initial imperfections to, and the reduction factor alpha h, which is the reduction factor for the height, while phi 0 is a basic value of 0.005, as you can see here. And this formula leads us to the final values of the equivalent forces to be considered in the design, accounting for the imperfections, which are, you can see here, for the ultimate limit state combination of 8.5 kilonewton for the current floor, while for the roof it's 7.6, and also the same kind of imperfections, or the equivalent forces accounting for the sway imperfections for the significant damage or the seismic load combination. As previously we designed the beams only for vertical loads, we will have to also have a primer guess of sections for the columns. And these columns may result from first check of second order sway effects. And here Eurocode 3 once again suggests that second order effects may be calculated according to the formula, or to the inequality of an alpha critic factor, which if it is under 10, the value of 10, and bigger than the value of 3, the imperfections must be amplified by an amplification coefficient, which is computed based on this alpha critical coefficient. You can see the formula here. And after a buckling analysis has been performed on the structure with the assumed column sections, you can see that the alpha critical here is around 7, which means that we would have to amplify all the imperfections, or all the equivalent forces that are coming from the imperfections, by a factor of around 1.18, which means that we are going to amplify these forces by around 17–18%. Having all of that taken into account, we can design the dissipative zones, which I believe that you paid attention at the previous presentation where Massimo has presented the formulas for the design of the dissipative devices. And here we can rely on the formula that is being illustrated on the right upper corner of the slide. And the M-slip design resistance of the joint corresponds to the onset of slippage in the dissipative device. And so we are going to account for the dissipative or to the friction resistance of the dissipative device to design the joints, such that the design resistance of the joints it matches the design bending I said previously, which is based on the operational limit state. And you can see that relying on the variation of the long-term preloading force in the high-strength bolts that are clamping the device to the haunch provided on the beam, we can reach the slippage resistance of these joints very close to the design bending moment. As you can see here, the values are very, very close. And in order to ensure a local hierarchy between the resistance of the joints and those of the beams, factor, which based on previous studies has been proven to be around 1.56 for dissipative devices of this type like FREEDAM. And so we are going to reach this kind of resistances for the beams, which are required in order to not reach yielding in the beams prior to the slippage in the joints. So in order to verify the beam sections that we previously we can rely on these three inequalities. So the bending moments in the beams has to be lower than, obviously lower than the capacity, the plastic capacity of these beams. The axial force has to be lower than 0.15 or 15% of the plastic axial capacity of the beams, while the shear force has to be once again lower than the plastic shear capacity of the beam. And you can see that based on the previous computations, we are ensuring these conditions to be checked, at least for the bending moment and for the axial force. While for the verification in terms of shear resistance, the things are a bit more complicated because the shear force that acts on the beams has to be computed based on the shear force coming from the non-seismic load combination, plus the component that comes from the overstrength of the dissipative zones that are at the end of the beam ends. So we can see that you have a component here for VED, which is the shear force, the design shear force, coming from the non-seismic actions, plus the component coming from the slippage resistance of the joints, where once again we are going to take into account an over-resisting factor of 1.50, and this accounts for material overstrength. And it has been already experimentally and numerically proved in previous researches. And you can see now that based on all of this, in a way, at first there were assumptions, now they are certainties. We can check the capacity of the beams in terms of bending, axial, and shear resistance. And based on the previous computations, we can stated before, we have to ensure once again the capacity design principles are the capacity design principles are respected. And here we are going to rely on the equilibrium on the nodes and on the overstrength of the dissipative zones that here are the FREEDAM joints once again. So we are going to rely on the slippage resistance of these joints, accounting also for a overstrength factor omega Rm. And you can see that by making this equilibrium, we are reaching values lower than the plastic capacity of the joints, considering the actual load in it in the columns. So we are going to assume that sections of HEB 300 and HEB 280 for the columns are going to fulfill these requirements. Please note that there are two types of sections for the columns, because we consider that the beams and the columns are the same for two consecutive floors. So, for example, the first and the second floor have the same member sections, while the third and the fourth, again, the same sections among the two. Another condition to be respected according to Eurocode A is to control the second order effects. And here the condition is that if the theta, which accounts for the second order effects, is lower than 0.1, the condition of controlling the second order effects can be neglected, while if it is between 0.1 and 0.2, they can be approximately considered by multiplying the relevant seismic actions by a factor equal to 1 over 1 minus theta. And you can see that for each of the stories of the structure, we achieved a theta greater than 0.1, but still below 0.2. Conservatively, and theta max amongst this story of amongst all the stories of 0.13 has been achieved. So we are going to use an amplification factor of 1.14 for the second order effects to be considered in the design. And the last check to be considered is the interstory drift limitation, and this can be most of the times, actually, at least in reinforced concrete structures, this can be a very demanding requirement, and a lot of designers they didn't check it, and while checking, they realized that they will have to change the sections of the members. And here you can see that the admissible limit, the admissible value is linked to the height of the story and to the coefficient that accounts for the sensitivity of the elements to the interstory drift. Here, the requirement in terms of interstory drift is given by the interstory drift admissible, which is 0.02 radians in our case, while the one that we achieved in the design, it's below this value, so that we can consider that the interstory drift limitation is being respected. Now that we more or less completed the design for seismic actions, even though I went through it very briefly, you can go in more details into using the deliverables of the project, because there are a lot of structures designed according to Eurocode 8 and according to another theory that is the theory of plastic mechanism control, which is also used in the seismic design. But I would like to go briefly also through some slides that may have a very significant influence on the overall response of these structures. And moreover, in robustness investigations, they could prove to be a key element to be investigated, because, for example, in a very rare seismic event or under a very severe accidental action, we can expect that the lateral loads or the requirements in terms of lateral loads would be great, and the joints would could or should prove to have sufficient rotation capacity in order to allow for these displacements, either lateral or vertical displacements. And so they are key elements in such investigations. Why we are talking about robustness? Because in Eurocode 0, Eurocode 0 states that a structure should be designed and executed in such a way that it will not be damaged by events such as explosion, impact, and the consequences of human error to an extent disproportionate to the original cause. And the next clause of the code says that we can reach such structures that are able to survive these events by avoiding, eliminating, or reducing the hazards, by selecting a structural form with low sensitivity to the hazard, or once again selecting a form and design which can survive the removal of individual or limited parts of the structure, so that the progressive collapse is not triggered, and also to avoid systems that collapse without warning, so that we avoid brittle failures. And the last requirement, which is one of the minimum requirements of the code, is to tie the members together, which means that we would have to provide a continuity between the members, horizontally or vertically. And after, the standard just refers the reader to Eurocode 1 Part 1.7, which is the Eurocode that deals with the design against accidental actions. And this design standard is defining the robustness as the ability of a structure to withstand events like fire, explosions, impact, or the consequences of human error without being damaged to an extent disproportionate to the original cause. So you can see the relation between the definition of robustness in Eurocode 1 Part 1.7 and the requirement stated in the Eurocode 0. And what means the robustness in this case is that once subjected to an exceptional event, a structure can, the structural response can evolve into two different scenarios. The first one, the structure or part of the structure can collapse, or the structure survives the event even though with permanent displacements, permanent deformations, and so on. And the questions arising from these two scenarios are how to prevent the collapse of the structure and how to ensure that the structure survives the event even though with significant deformations or damages. And the answer to these two questions is the robustness. It's given by the concept of robustness. And in order to design a structure for robustness, Eurocode 1 Part 1.7 provides the designer with two main categories of strategies for design. And the first category are strategies based on identified actions. So we are identifying an accidental action, and you are designing explicitly the structure to resist this action. While the second category of strategies is based on limiting the extent of localized failure, meaning that in this category of strategies, with this category of strategies, you are going to cover a wide range of possible accidental events. Therefore, it is of main interest when we are designing the structures to be robust. And you can see that there are three main types of strategies in this category. One being the enhanced redundancy, meaning the alternative load paths, or to ensure that the structure exhibits alternative load paths. The second one is the key element method, and the third one is the prescriptive rules, which here we can already think about the tying method, which is the one intending to ensure that continuity between the elements of the structure, as I said previously. So we are ensuring tying resistance to the elements. However, in order to design a structure explicitly for robustness, we are going to rely on the concept of consequence classes, which is introduced in Eurocode 1 Part 1.7. And here the structures are categorized according to their occupancy and their height and the risk that is associated to their failure. So according to this table that is provided in Eurocode 1 Part 1.7, we can conclude that our structure it's class 2A or lower risk group structure, and therefore for this consequence class structure, the code prescribes minimum requirements for robustness, and this is again the prescriptive rules, which implies that we have to ensure the structure with horizontal tying or horizontal tying resistance. Anyways, if you are going to study a bit the deliverables of the project, you will see that in the project we designed structures with 4 stories and 8 stories, and those ones with 8 stories are classified as CC2B structures. And for this class of structures, the code requires to apply the notional removal of supporting elements method and to demonstrate that the structure can provide sufficient and adequate alternate load paths in case of these events, so that the structure survives the removal or the loss of a supporting element. And we are going to apply this method because it's one of the most exigent requirements in terms of resistance ductility for structures. And we are going to apply it for the frame that has been previously designed for seismic actions. And here we are going to assume that a column loss occurs at the base floor of the building, of the frame. And you can see that it's marked in red here on the plan view and here on the elevation of the structure. And from the theoretical background, we can already expect that the structural response would look in the following manner. So the structural response in case of a static column loss can be assumed as a 3-phase process. The first phase corresponds to the situation when the column is subjected to the normal axial force, which is called normal because it's the axial force that is normally applied to the column in the accidental load combination. And the phase 2 starts when the column is beginning to be lost, meaning that at first the column is removed statically once again. And you can see that you will have a first branch of behavior in this phase 2 being elastic, while at a certain point the stiffness drops, and it corresponds to the first formation of the plastic hinge. While at the end of plastic 2, we reach a global plastic mechanism in the directly affected part of the structure. And this continues with a phase 3, which corresponds with the development of significant displacements in the structure, and also the occurrence of significant second-order effects. And also, you can see that the catenary action that develops in the beams of the directly affected part, it's ensuring if the beam ends or the connections that are provided at the beam end are resistant enough and ductile enough, the catenary action that develops in the beams can provide alternative load paths to the loads to be distributed to the rest of the structure, and so the structure can survive the event, reaching, you can see here, reaching a point where the response corresponds to and the equilibrium. So the structure reaches an equilibrium in a large displacements, large deformation field. And this response can be investigated to a push-down analysis that can be seen as a pushover analysis, with the main difference that the load is here applied downwards, so it's a vertical force. And in order to simulate the column loss in a frame, we can simulate it by replacing the column with a reaction, which is here ND or N normal from the previous slide, which corresponds to the axial force in the accidental load combination. And after that, applying at the same node, at the upper node of the lost column, an incremental force ND, which is applied downwards, so that we remove statically the column. And if the ultimate force reached by amplifying the ND with the lambda, which is the load factor, reaches a level which is higher than the normal axial force in the accidental load combination in the column, the structure can be assumed as robust, while if the ultimate force that is reached further to the column loss in the structure is lower than the normal actual force in the lost column, then the structure can be considered as not robust enough, and so the collapse is triggered. So we did this process for the analyzed frame, and you can see that here the response of the frame is. Sorry, I continue to hear noises. That's why I'm a bit confused. You can see here that the response of the structure on the right hand side of the slide, the response of the structure ends. I mean, we have the failure of it at around 430 kilonewtons, which is lower than the normal actual force in the lost column, meaning that this structure is not robust enough. And why it is not? By investigating the results of the analysis, we identified that the failing component is the friction device, because the bolts that are now acting in shear, they are engaged in resisting the shear, they fail prematurely, so they diminish significantly the overall ductility of the structure. And so a solution to improve the post-slip behavior, meaning that after the joint has slipped or has reached the end stroke, the so-called end stroke limit state, meaning that the bolts are getting into contact with the plate here, with the end of the slot hole. Only 2 bolts are going to be engaged in resisting the shear, while the capacity of 2 bolts in shear is a lot considerably lower than the resistance of any other plate components in the joints. And this brittle failure doesn't allow the structure to undergo higher displacements, and so to develop significant catenary reactions. And the solution to improve the overall behavior of the structure has been identified, and it consists of changing slightly the configuration of the damping device, meaning that we added 2 slotted holes in plus here. So we changed the configuration of the slot in the device, and this ensures that at the end of the stroke, we are going to engage four bolts in resisting the shear, and so to increase the overall resistance of the device. And you can see that the response of the device, it's not tremendously enhanced by doing this, but when we integrate this change into the structural model of the building, you can see that the difference is huge, meaning that if previously we reached a resistance of 430 kilonewtons, now we are going above 800, which is almost double than the one with the initial configuration of the joints. And here we can assume that now the structure is robust enough to withstand the assumed column loss. And even though the collapse occurs once again as a result of the bolt rupture and shear in the FREEDAM devices, some plastic deformations also occur at the beam ends, meaning that we reached the plastic resistance of the beams also, and this is reached predominantly at the first floors of the structure. So in order to conclude, because I see that I'm reaching the limit of the time, here we went through the design of moment resisting frames equipped with FREEDAM joints, and it was previously designed for seismic actions. And from actually what I've done for this structure in particular, I designed it for robustness. So I think that you could notice that during my presentation that I was going more in detail for the robustness part. However, the FREEDAM joints allow the structure to dissipate the energy, the seismic input energy, through friction in the damping devices. And so they lead to less demanding requirements according to the seismic capacity design principles. Less demanding requirements for the columns, and also You can see in the deliverables of the project that there were designed multiple structures, MRFs, and also dual concentrically braced frames. And I think that those work examples are going to make it clearer for you what the seismic design of this structure means, and also what means the dissipative capacity of the joints for the seismic performance of structure. While the robustness investigation that I presented here revealed that the initial configuration of the joint as proposed has not been properly tuned for robustness purposes, and you saw that the structural response of the building equipped with FREEDAM joints at first was not adequate for robustness investigations, while after the slight modification of the dissipative device, we reached adequate response and the structures were robust enough to survive the event. So thank you very much for your attention. Sorry if I went a bit more than what expected.
No problem. You did it well. Oh, there is an echo. Please, are all the microphones muted? Yes, no, you did it well because you had really many things to say in a few times. So thanks for illustrating this design. I would just to emphasize again that to reach the robustness of a structure is not always a problem of supplementary cost. You see that sometimes the detailing, and especially the detailing of the connection, is just enough to be robust or not to be robust. Anyway, we come now to the last presentation, which will be made by Jean-Francois Demonceau, my colleague at the university, who is associate professor. And he will just tell us how we can practically design the FREEDAM joints. We know that the design of connection is sometimes time-consuming, so it was important to provide to the designers tools which allows to minimize the time for design. So he will explain what has made available inside the FREEDAM Plus project. So the floor is yours, Jean-Francois.
Thank you very much, Professor Jaspart. So, as we are a little bit out of time, I will try to be brief by presenting the different tools which are nowadays available for the design of the FREEDAM connections. The presentation will be subdivided in 4 parts. I will briefly address all the different design tools which are nowadays available. And then I will present the main design tools which is related to an application which is freely available. Then I will briefly address a worked example and then come to some conclusions. Regarding the design tools, the first tools that we think about is the design manual which is available on the ECCS website. In fact, just before starting my presentation, I put a link on the chat. So you can directly click on this link and get access to the ECCS website. And on this website, you will see that you have access to what we call the FREEDAM Plus document. And for this FREEDAM Plus document, which is available, as we already said, in 13 languages, you will have all the details about, first, the technical solution we are proposing with the FREEDAM connections. How this solution has been validated at several levels, at the level of the dampers, at the level of the joints, but also at the level of structural behavior, but also all the design process for the calibration, the tailoring of all the different joint components included in the FREEDAM joint solution. And all the design process for the FREEDAM joint solution is fully in line with the philosophy proposed in the Eurocode. I mean, it is based on what we call the component methods. Then, as a second aspect related to the design, and I think it's part of the tools which is available, it has already been mentioned, but you have to know that the FREEDAM joints we are proposing through this project will be directly implemented in Eurocode 8, and in particular in the list of pre-qualified joint solutions for steel structures submitted to significant seismic loading. And so it will be reflected in a specific annex where this joint solution will be proposed. Another tool which can be useful is related to the YouTube channel and ResearchGate webpage that we also developed. So I will just show you briefly what is behind this YouTube channel. In fact, in this YouTube channel, you will have a general introduction to the FREEDAM joint solution. This is the video which was shown during the coffee break, but you will find a lot of small videos demonstrating the way we validated the different parts of the joints, or even the complete joints in itself. Videos about experimental tests performed in different laboratories, but also videos showing some numerical simulation we perform in the framework of the FREEDAM Plus project. So I'll come back to my presentation. Okay. For sake of completeness, I put also the link to the YouTube channel on the chat right now. And the last tool which is nowadays available, and it is probably the one you will use more directly if you intend to implement the FREEDAM joint solution in one of your structures, is the user-friendly software that we developed. This user-friendly software is available on different platforms. It's available on the PC, okay, in the framework of an interactive web page. But also, we decided to propose this application on Google Play and on Apple Store. So it means that you can have this application on your mobile, smartphone, even tab, numerical tab, and so on. And you will see that this tool is quite simple to be used. It is the main page of this tool is divided in 4 parts. The main part, which is related to the calculators, it is where you will be able to compute the FREEDAM joints. The second part, which is a part dedicated to catalogs, where the main properties of the different profiles that can be used with the FREEDAM joints are provided. Then a reminder of the different partners which are being involved in the FREEDAM joints project and which have contributed to the validation of these solutions. And finally, you have the main suppliers for the FREEDAM joints connection, which is FIT company, which is an Italian company. Also, on this app, you have secondary options where you can have links to the different web page that I mentioned previously. But of course, as in all applications, you have access to a user manual which explains you how to use the application. Now looking to the main part of the software, which is the calculator, you will see that this calculator is subdivided in 2 parts. The first part is dedicated to 5 industrialized FREEDAM kits. In fact, we are proposing to this application the use of 5, we could say, pre-qualified, pre-designed FREEDAM connections, which are valid for a certain range of beams solutions. So as you can imagine, and I just mentioned it, as they are pre-qualified and pre-designed kits, they are linked to some assumption that should be respected. The first one is that only S355 steel grades can be used for all the members. The considered cross sections for the beams are limited from to IPE section going from 270 up to IPE 750. The slip coefficients used for the friction dampers is the one which is reflected here, 0.53, which is related to a specific material which is used for the friction pads used in the damper. The range of preloading which have to be introduced in the bolts of the friction dampers are limited between 40 and 60% of the full bolt preloading as recommended in the codes. Why we are coming to such small value? It is just a way to ensure a good behavior of the friction damper under cyclic loading and to ensure that the dissipation of energy during the earthquake will be constant and regular and without any problems. And the fact of reducing this preloading was the best way to ensure a good cyclic behavior to the connection. You see also that the solution which is recommended in this application is related to the solution with the vertical dampers. You saw through the presentation that we were also investigating what we call an horizontal damper, but this one is not introduced in the application. The ball should be of grade 10.9, which is quite classical for pre-stress balls. And last but not least, the utilization factors to be considered for these joints should be between 0.3 and 0.6. These utilization factors reflecting the relation between the bending action at the level of the beam and the plastic resistance of the beam. Okay. Here are the 5 FREEDAM kits which are industrialized and which are proposed, and you see that the differences between the different solutions are related to the number of balls which will be used at the level of the damper. Differences also around the ball diameter which is used and about the dimensions of the hammerhead which is connected at the bottom flange of the beam. So here is a table reflecting the solution which will be proposed if you use the application. And you see that according to the utilization factor that you will consider and according to the beam which is connected to the column, you will come to different kit solutions which are proposed for your structures. This was the first part of the calculator. The second part of the calculator is dedicated to customized version, which means that you can decide to tailor your specific FREEDAM joint solution. And there, for sure, you will have to introduce additional information in comparison to the one which are required for the pre-qualified, pre-designed FREEDAM kits. But anyway, the software allow you to define your own FREEDAM solution going outside the range of validity of the previously presented FREEDAM kits. So here is a worked example which is proposed in the presentation, but I think that as worked example, the most easiest way to proceed is directly to show you how the FREEDAM tools is working. Again, for sake of completeness, I will add the link to this application on the chat. And so if we go in the calculator, you just click. We will use the industrialized joints. You have to select the beams that you are considering for your structures. Let's assume that we will consider the IPE 500 beams. You have to select the steel grades. You see that for the moment we are limited to S355 steel grades. Why? Because I see that I have a question on that in the chat. Why? It's just because the solutions have been validated through in the framework of the FREEDAM joints for the steel grade, in fact. Knowing also that in terms of overstrength, possible overstrength with this steel grade, the overstrengths are quite limited. While if we are coming to the use of S235 steel grades, the overstrength of this material could be higher, and it leads to a significant over-design of all the non-dissipative part of the joint, which is not really economical. So that's why we're coming to these steel grades. But you see that in the software, even if for the moment we can only select one steel grade, we think that one day we could extend the steel grades to be used for the FREEDAM joints. And nowadays, the tendency of the Yule code is to go to higher steel grades. So why not to go one day up to S420 or S460 steel grades for the FREEDAM joints solution. So section of the steel grades. And then we have at the end to select the utilization factors. Let's assume that the bending loading is equal to 50% of the plastic resistance of the beam. We select this one. Then you have just to put on calculate, and then you have a summary of the FREEDAM kits which is suggested by the software. It is the kit D2B with the main properties of this kit, number of balls and so on. The preloading to be applied at the level of the balls of the FREEDAM damper. And if you want to have more details, you have just to push on full report, and you have directly a PDF file with the complete report with all the details of the kits which is proposed and all the details about the main computations which have been performed for the definition of the FREEDAM kits. So, in conclusion to this small presentation, nowadays a user-friendly tools for practitioners is made available on the web, but also through the different stores on smartphone. The tool allows the use of pre-qualified FREEDAM joints or the use of customized joints. And last but not least, the tool is available for free. So you can easily download it through the stores if you want to install it on the smartphone, or you can use directly the tools through the links I just sent on the chat if you want to use it through your web browser on your computer. So thank you very much for your attention.
So thank you for Jean-Francois. I see that we are only 5 minutes late. It's almost perfect, even if I have obviously officially to apologize for this 5 minutes. So I would suggest now that all the speakers open their camera and they open their microphone in such a way that we can start the questions, the discussions. And I so welcome all the questions which could come from the participants. The first question was about the use of 235, but you already replied to that.
At least I tried. I don't know if I was clear.
But maybe the person who asked has maybe to comment your reply.
But I say a thank you, so it means that most than probably I was clear. No questions? Because if you have no questions, even if I was in the project, I have one for Massimo. Because I participated to the FREEDAM workshop also in France last week, and one of the questions which came out from this workshop was related to the cost of such a joint solution in comparison to more classical joint solutions. Can you provide some ideas about the cost that such a solution could represent?
This is the typical question, I think. And I think that in many workshops it was coming the same question. So now we are doing also some case studies. So we for sure we know the production cost from the test that we have performed, and now we are also doing this pilot project. So we will have also one of the objectives is to provide information related to the cost of the joint in relation to the cost of the whole structure. For sure, the joint is, I think, is easy to understand, which is more expensive than more simpler partial strength joint or full strength joints. So for sure, the cost will be higher. But this type of connection has to be seen as a kind of device also. In any case, the estimate for a typical layout of this joint, let's say the D2 device, D2A, which is average size, let's say, is about 1,000 euro. And clearly the application for which this typology is thought is for a perimeter frame. So for a structure where internally we have all gravity columns, so simple joints, and on the external skin of the building we have few friction joints, because obviously we don't have to increase too much the cost of the structure, and we don't want to complicate too much the construction with many expensive joints. So in any case, if we look for the pilot, like we can anticipate also some numbers, but we have about 50 joints. So it's an overall cost of 50,000 euro for the whole building. but the cost of the buildings for the tender, the bid that we will do, is about 3.5 million euro. So I think it's really relevant, actually, in the perspective, if we consider also the objective that we can achieve with this solution. I think it's really meaningless to think too much about the cost, because it's a cost of a small part of whole structure and the whole construction, which is has also the complementary parts, the walls, partition walls, ceilings, floors, everything. So I think it's really a small, it's not a big deal, I think, the cost.
Thank you, Massimo. I think it's clear, but there is also another aspect, is the fact that with such a solution, as we are coming to solutions with almost no damage in case of earthquake, for the insurance, it could have also somehow an impact. I'm pretty sure that nowadays the insurance are not really considering this aspect when they're fixing the prices of the insurance, but in the coming future, maybe this type of aspect could be accounted for, and then, okay, at the beginning, when you build your structure, you have some extra cost, but then you can save some money later on with the insurance, but also with the cost in case of earthquake, the cost of reparation. Yeah.
I think that's fully correct. Obviously, we have to see a little bit long term in this moment, because immediately maybe it's not in everyday life now, but I think that in few years it will become a benchmark.
And the robustness which is ensured through these joints is also from a long-term cost of concern, because obviously the aim there is to avoid to have a person, let's say, who suffer too much or who dies through the event. So this is also, I think, an aspect which has to be underlined. Nowadays, we are not maybe too much paying attention to that, but progressively this comes, and this has to be satisfied in more and more projects now.
Yes, I think so.
Other questions from the floor?
I'm pretty surprised about the numbers of attendees to this webinar. It's a large number, I think.
So they seems to be quite interested by the topic, but I think they have maybe few questions. I mean, everything was clear, probably. I think André Plumier is requesting the word.
Well, it's not exactly a question, it's a remark. If I can share my screen. It's in the design example by Golea, there is this expression for the check about columns. Now, I know it's difficult because the document to which he refers is still evolving, but there is only this omega RM which takes into account the randomness of material which is provided on site. But this formula has evolved recently, so there is an omega strain hardening in addition. So I just say this so that in the documents that you finalize, the thing be correct. If there is a problem, now it's too fast now to, let's say, give an answer to this, but I think that there may be a problem.
Yeah, that's always the problem when we try to be up to date. We are using the latest draft of the norms, but as you are saying, these drafts are still evolving, and so for sure, maybe at the end, when everything will be fixed, we will have to make an update of the worked example, I think. Yeah.
I would like also. Yeah.
Yeah, well, this has logic because in this expression which is shown, there is not this 1.3 of the classical formula. Now, the omega RM may take that into account, but you have a strain hardening is not in. So, as you say, this should be corrected at a later stage. So we are close to the to the final stage with this document these days.
Yeah.
Okay, thank you.
Thank you.
I am just checking the document, and it seems that in the meantime it has been revised. So the result that I was reporting, they might be for a previous version of the document.
Yes, but for those who would not know it, when the code is revised, because we are close to these revision committees,
Yeah.
it may change from one day to another day. So it's difficult.
Well, this last document that I have shown is from the end of March this year. So that's only, you know, not even 2 months ago. So
another aspect I wanted also to raise is the interest of the partial strength joints, because nowadays the overstrength factors has also been modified. And now for high strength steel, you can even raise 0.45. This is really huge. So when you have to design a full strength joints for such an overstrength factor, it becomes almost impossible. So I think that this is a nice reason to promote now the partial strength joints as the FREEDAM ones.
That's correct.
So, are there questions from the audience? So, if not, I think it's just in time. It's 5 o'clock, so surprisingly, we are now just in time. I hope you enjoyed this seminar. I would like to thank you, obviously, for attending it. I hope that it is in line with your expectation. I would like just to say that you have never to hesitate to contact us. And when I say us, it's obviously in Liège, but also all the other persons who were the speakers today. If you need some further explanation, or if one day you would like to have advice possibly for the use in one of your projects. So never hesitate to contact us. You have our coordinates. So if nobody has a last remark to do in the audience and in the speakers, I would then close really on time this seminar, and I would like to wish you all a good evening. So, bye-bye.
Thanks a lot, everyone.
Thank you. Bye-bye.
Bye-bye.
bye.
Bye.